Okay, let me begin the third class meeting of EECE574, Probability and Random Processes for Graduate Students. So the handouts, annotated handouts and lecture videos are now available at the primary course webpage at my lab homepage. Many students ask questions about passwords. They are lowercase English characters, 1, 2, 3, 4, etc. Okay, ONE, blah, blah. There is no 40, but you should remember 40 is FORTY, not FOURTY, but we will not have any 40 for the password, so it's okay. Homework number 1 was due just before, and it seems that some of you do not have the Peebles textbook, so whenever I give you the exercise or example problems from that book, I will post it on the PLMS. Do not share with outside class students because it may sound or seem like copyright infringement. So, okay. Here goes the corrections, clarification, common mistakes, misunderstandings, misconceptions, myths, frequently asked questions part. And today there was no mistake, but I want to mention some very important meaning of some notions we've learned last time. So the first thing many students have trouble is this. Also, when I was a graduate student, I also suffered from this misunderstanding. First thing, consider a continuous time random process. Many of you who already have taken an undergraduate course or you have been exposed to the notion of continuous time random processes, you are likely to consider a continuous time signal defined on the entire real line, which means that the t ranges from negative infinity to positive infinity and with uncertainty. So you may have conception like that. A CT random process is to model a continuous time signal expanding the entire real line with uncertainty. That is not correct. That is only a part of the story. Of course, in many cases, you are handling such a continuous time random process where t ranges from negative infinity to positive infinity. However, there are many applications and many cases in your graduate study or research where you have, for example, a time-limited continuous time signal. By the way, given a time-limited continuous time signal, how many time t instants do you have? Still uncountably infinite, okay? So what I'm saying that a CT signal or CT random process have uncountably infinite random variables or numbers, that does not come from the fact that t ranges from negative infinity to positive infinity. Even if we limit the time interval to a finite length, still we have an uncountably infinite number of variables or random variables, okay? So be careful. A CT random process, as I define, has an uncountably infinite number of jointly distributed random variables. And that may be defined on a finite interval or an entire real line, okay? So be careful. Second, now let's consider a similar case where we have a discrete time random process. And you may have already seen that dt Fourier transform and a discrete Fourier transform looks very similar and often quite practically interchangeably used, right? And even some of you may ask, what? Aren't they the same? Something like that. And when I asked the ChatGPT to list up the kind of course outline of signals and systems course, I found that the ChatGPT at that time could not distinguish discrete time Fourier transform and discrete Fourier transform. So you may try that. Anyway, similarly, given a discrete time random process, in many cases, you may say that, okay, in an engineering sense, I'm given a vector, I'm given a random vector in many cases. However, mathematically speaking, when we have a countably infinite number of random variables, we have two cases in most of the times. First one is that our time index ranges from negative infinity to positive infinity at, for example, at every integer. Okay, and that kind of signal with uncertainty may be modeled as a discrete time random process. However, there is another one that is very, very important, especially when we consider convergence of something uncertain. That is the notion of a sequence of random variables. So these two are different in this way. So when you have, for example, in measure theoretic sense, I have to use this type of notation for random process, right? Here, S is the argument of this function or mapping rule or selection rule, and S comes from, S is the outcome or realization of a random experiment that is described by an abstract or underlying probability space. Here, a DT signal has T, for example, a map, T is a member of the set of integers. For a sequence of random variables, T may be an element of the set of natural numbers. Or after some mapping, it may start from 0 to infinity. It might start from some negative n naught to infinity. But anyway, the difference is that this one is kind of bilaterally defined, and this one is unilaterally defined. And you may say, what's the difference? Actually, there is some difference, because when you think about convergence, in this case, you may think about convergence of something when t goes to negative infinity and also to positive infinity. But in this case, if you go to 0, just 0, right? You can only consider the limit towards the positive infinity. So that's the difference. Okay, so whenever you have a countably infinite jointly distributed random variables, you have to decide which one to choose and which one is more convenient for you to handle. Sometimes you model your signal as a discrete time random process. Sometimes you model your countably infinite number of random variables as a sequence of random variables starting from some finite number to, for example, positive infinity. Another one is this kind of thing. Definitely, you have a finite number of jointly distributed random variables. However, you don't know what would be that finite number. In that case, sometimes we just, for convenience, model that case as a discrete time or a sequence of random variables. For example, consider this case. Suppose you observe the stock market index of today, or especially you observe the Samsung Electronics price at Kospi, and you ask the server located, for example, in Yeouido, Seoul, to send you the updated information whenever new transaction or new sell or buy occurs. The problem is that if you ask in that way, you don't know in a specific day how many transactions or that kind of buy and selling numbers will occur. Sometimes if everybody got into a panic and there are a lot of panic sales or panic buy, probably you will receive much more results or sequences of transactions, for example, today. However, tomorrow, that is a national holiday, there is 0 transactions, right? So in that case, you don't know the exact number, but you know that the number should be finite. It can't be countably infinite, impossible, right? But in that case, it's harder to decide the number. Of course, you may say that, okay, according to my experience, the number of transactions does not exceed 1 million. But if you program like that, and one day there are too many transactions, your program for automatic purchase and selling of stock may crash. And you will find after your vacation at Bahama that your bugged program sold every stock in the lowest price and you are bankrupt, right? So in such a case, it would be better to model your observation as a sequence of random variables or a discrete time random process. So here motivates us kind of practical interpretation or engineering sense interpretation of infinity. That's what I want to say in the third part. So what do we mean by, for example, as n tends to infinity or as n goes to infinity in mathematics? How can we interpret as an engineer that kind of mathematical description or statement? That is this one, for sufficiently large n. Okay, this is our engineering interpretation of this mathematical expression. Got it? So in many cases to us, infinity does not mean infinity. Just it's the convenience for some replacement of sufficiently large some number. Got it? So you have to have this in your mind. Another one is this one. So here goes, I'm sorry about this Korean character because my keyboard and OS does not give us this inverse slash. But anyway, this is from the grammar of the programming language LaTeX. And here what I meant is that the T is a member of negative infinity and positive infinity. So suppose we are given something like this. Okay, here means that the T is either negative infinity or positive infinity. And you may say that something's wrong, but in that case, you may consider this. This is the extended real line that includes all real finite real numbers and positive infinity and negative infinity. So you kind of extended your notion of the set of real numbers. In that case, anyway, you have some infinity there. And what does that mean? Mathematically speaking, you may say that, okay, it could be positive infinity or negative infinity or any large number or any small number. However, some of you who are Christian or who are Jews, who are Muslim may say that, wait a minute, there was a creation of time, right? And there will be the kind of judgment day. So T cannot be ranging from negative infinity to positive infinity. Or you may say that, okay, even though there is some God who started our time from negative infinity and will end at positive infinity. Anyway, the lifespan of our human being would be finite. In that case, what's the meaning of this plus minus infinity? You are right. So in many engineering sense or practical sense, this negative infinity means what? Sufficiently far past. And positive infinity means sufficiently far future. But this sufficiently far past and future may vary in many cases. For example, suppose you have your cell phone. And suppose you turn off every night and turn on every morning when you wake up. Now, how can you for example, record the power consumption of a cell phone. And how can you interpret that? You may say that, okay, I may assume that 9 a.m. to 9 a.m. plus 1 microsecond is enough to model that t ranges from negative infinity to positive infinity. Got it? Or for some applications, you may say that, okay, my negative infinity could be the year 1900, and positive infinity means 2050, right? So according to your application, this positive infinity to negative infinity may represent a very short period or sometimes very, very long period. It all depends on the situation. And you choose this infinity just for convenience. However, it shouldn't be arbitrary. When you model something, including plus minus infinity or infinity, some other people may object to your choice, okay? So be careful. Now, given that kind of clarification, let's go back to the kind of dilemma of this Kolmogov's existence or extension theorem. So I emphasize the importance of Kolmogov's existence or extension theorem. And many textbooks of even the graduate level does not mention this that much. But I believe that is the most important theorem, even though we have no capability, I have no capability to rigorously prove that theorem, but I can provide a good interpretation for you and also remove some misunderstandings from that based on my experience of a lot of bumping around. So Kolmogov's extension theorem, first, it means that a random process, the notion of random process, if we have started it as a countably or uncountably infinite jointly distributed random variables, still can be put into that measure theoretic framework of defining every random something. For example, defining a random variable measure theoretically is very straightforward. You have a random experiment that generates some outcome. And this random experiment or random source is governed by, the entire rule is governed by some abstract probability space. Now you have a deterministic measurable mapping rule called capital X of S. And the output of this box, this deterministic mapping rule, is what now? Your conventional random variable. So you enclose these two boxes into one, and then you have your undergraduate understanding of a random variable. So that's good. For random vector, you can still do that. Here is a random source. Here comes out a sample. And you have what? A box where there is a deterministic rule. For given S, you choose a vector and generate, right? That is a measure theoretic definition of a random vector. Now, how can we model a random process measure theoretically? And this is the block diagram you have to remember. And I will repeatedly draw. So even though our textbook prefers some notation like this or like that, depending on the preference of T coming first or S coming first, actually many people, when they talk about a discrete time random process and continuous time random process at the same time, especially in a measure theoretic sense, they love this notation. Okay. And here, the first box is a random something generate. And second one is a deterministic rule of selecting the output. So given S, if this T ranges, T is a member of an integer, then you may say that actually your outcome given some specific S0. So if this is S0, then what do you have? Sorry. X sub t of S0, where t is an integer, means that actually how many of x's do you have? Countably infinite. Because you have t in the set of integers. T0, T1, sorry, x1, x2, x3 given S0, and x -1, x -2, dot, 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 up to any number, right? If you have t a member of the real or every real number, then what? Given single S0 outcome, you have how many? Uncountably infinite numbers, right? That is parameterized by a real number. Got it? So first important implication of the Kolmogorov's existence theorem is that even a random variable, that sounds very strange, can be well put into the framework of major theoretic definition. So why people say existence? Given countably or uncountably number of jointly distributed random variables, Kolmogorov said that this function or that function exists. Got it? But here comes misunderstanding or something uncomfortable idea. Okay? But before I talk about that, I have to mention again. So this thing gives us another idea. Here, if S0 is fixed, then what? What is this in this case? This is a given S0. This is what? A deterministic discrete time signal, right? So given a specific x0, you have a deterministic signal. So kind of in this box, there is a person residing here, me, for example. And here is, for example, God. Okay, let me use lowercase God because it could be any God. And here, me, Professor Cho. And if I am given some S0, I have a jar of or collection of many sample paths. And given S0, I find, okay, which one is labeled as S0? And I find it and give it to you. And you are here, right? And in order to be more neutral, I may write this. Okay. Well, you are there and you observe. Okay. And this is the major theoretic definition. Be careful. This may sound like, as here I say, world is deterministic. Okay. Some God has selected S0 and some angel have chosen a function that would range from negative infinity to positive infinity already. Okay, you may interpret that if you wish. Got it? And also this interpretation is sometimes very convenient. Okay? So the notion of sample path is very, very convenient. And let me say why. For example, many of you know or already have an experience that, for example, our weather forecast says that today the Pohang area will have rain at 3 p.m. with probability 80%. What does that mean? What do you think that means? So I wondered how they computed the probability. And when I was at sabbatical leave at Florida, they had a lot of hurricanes. And actually, the weather channel, the United States has so-called weather channel. And if you tune it to the weather channel, all day long, 24 hours per day, 7 days a week, every time they talk about weather in the world, in your area. And when there was a hurricane, there was a kind of weather.com researcher explaining how they computed that percentage of hurricane hitting, for example, Gainesville area. And it was quite interesting. They said that they had a computer that simulates the weather. And they have, for example, balloons that measures the pressure, humidity, and the wind speed and everything. And they put it in their simulator. And they run, for example, for entire 24 hours of today. And it generates some paths, for example, right, about rain. Okay, so for example, this is time index from 0 today and 24 hours, right? And then here is the precipitation, and then 0, 0, 0, and some single simulation so shows some rain, right? For example, no rain, rain, no rain, or if this is amount of precipitation, that some 0 milliliter and increasing and decreasing, something like that, right? And then what they do is that they change or perturb their data because what they have from the balloons and every measurement equipments may be corrupted by some noise. So they model the noise and intentionally perturb the parameters. And as many of you already know that many differential equations or partial differential equations kind of when modeling the weather are nonlinear. And small perturbation may generate huge difference. For example, you perturb somehow, and then it shows that a lot of rain early in the morning, and the rain persists throughout the day. Okay, another simulation. And you perturb by randomly generating the noise, and then you have a lot of what? Sample patterns. Okay? And then at a specific time, 3 p.m., they see what? Random variables now, right? As I told you, if you specify t, you fix t, then what? It's a random variable, right? So now you count that number of occurrences where you have rain. And if that is 80% of all, then they declare in their web page saying that weather.com forecasts that at 3 p.m., the probability of rain is 80%. So this notion of sample path actually governs the weather forecast. Got it? So it's a very important concept. If you are an undergraduate student and you studied the concept of random process, probably you have had difficulty in understanding the notion of sample path. And even though you believed you understood the notion of sample path, somehow it would kind of oppose to your feeling, right? And what I want to say is that that is a convenient method, okay? It's not the only way. That is a convenient method to understand what is going on, okay? Sometimes that is very useful. Sometimes the sample path concept may confuse you a lot. Then at that time, you just discard it. Got it? So I covered up to this one. Yeah. So the Kolmogorov extension theorem does not say the world is predetermined. Okay. Consider a continuous time, especially a continuous time random process ranging from negative infinity to positive infinity. According to the Kolmogorov theorem, this statistical modeling may not mean anything because, for example, God has chosen as 0, and I have given you the entire continuous time signal that you will observe just once, right? Because time ranges from negative infinity to positive infinity. How can you live twice and observe some random realization? So what I mean is that sometimes that kind of interpretation may be okay, but you have to remember negative infinity and positive infinity may mean for sufficiently small time past and sufficiently large time instant t. Got it? So all approximations they are. By the way, for deterministic random processes, this notion of sample path may be very, very powerful. And we will go back to the slide soon. And another notation is like this. When you are a high school student preparing for the college entrance, probably you've read a lot of popular science books, and some of the books may have interpreted the quantum mechanics or quantum principles as parallel universes existence, something like that. You may interpret this Kolmogorov's extension theorem as that. For example, you model a continuous time random process. T ranges from negative infinity to positive infinity. Even though that means if you exactly follow this figure, if you live in this universe, you observe a single deterministic, already have chosen a signal. However, in some parallel universe, you may observe different sample paths. Okay, but I do not support that idea. Yeah, it's I just believe that that is a mathematical convenience, not the real thing. But anyway, I'm not a physicist. So anyway, so remember that infinity and infinity related everything, including continuous time signal when you were taught in signal-gen systems, discrete time signal you taught in undergraduate signal-gen systems, they are all approximations. Got it? Whenever you see infinity, they are all approximations. However, we need that in many cases. For example, you consider a growing internet, and you want to know what will happen if the number of hosts or number of links, number of routers doubles, triples, quadruples. In that case, if you consider every situation possible, it would be impossible to analyze. In that case, what do? You take, okay, as the number of links, number of hosts, number of routers tends to infinity with the number of nodes divided by number of links, number of routers divided with number of users are fixed as alpha and beta. And what will happen? In that case, you may say that you may have a very nice result, some number that converges to a function that is determined by alpha and beta. In that case, you may say that, okay, if the number of nodes increases with alpha, beta fixed, then something happens, probabilistically or deterministically. So infinity is a very convenient mathematical tool for engineers. Got it? So remember that infinity may confuse you a lot, but it would be your best friend. Got it? Okay. So introduction was very long. Let me go back to the overview of this course. So I'm going to follow this kind of second part of our textbook, not the first parts. So we are covering this general concepts part, general concepts of random process. But I use the handouts from my undergraduate course, where when I teach that, I taught that I had to cover very fast due to the fact that I talked too much about the random variables and vectors part. So in this course, I reduced that part and will focus more on random processes. And then may be more benefiting you, given that our department now allows every graduate students even to take 300 level courses. If you believe you lack of some knowledge on random variables and vectors, please take that course with this course, okay? We have that course in this semester, taught by Professor Kim. Got it? So after we cover general concepts, and we will go back actually to the sequence of random variables. According to our textbook, this comes first, sequences of random variables. But I hate that. Personally, I believe you have to be given the concept of random processes, whether it is discrete parameter or continuous parameter, and then you have to study a sequence of random variables as a special case. So I'm going to cover it later, got it? And then we will talk about random walks and spectral something. Got it? Okay, review. Non-major theoretic definition of random processes. We mentioned in the first class meeting, major theoretic definition of random something in the second class meeting. And I believe you have better knowledge now than you come to this course. And Kolmogorov's extension or existence theorem is very, very important, especially when we talk about sequence of random variables. When we talk about different modes of convergence of a sequence of random variables. Probably you remember convergence, almost sure sense, convergence in distribution, convergence in probability, convergence in the second mean, something like that, in your undergraduate course, and you had no idea at that time, even though I taught you, some of you, in the undergraduate program, and I'm kind of sorry about that. So let's have a better understanding through this course. Okay. And also we've seen how we can characterize a random process. By using what? By using what? Yeah, nth order joint CDF or PDF. And by the way, Kolmogorov's extension theorem proves the existence of such mapping or selection rule in the this second box. Okay? It does not say that you can actually find that function given any random process. In many mathematical theorems, it does not give you how to find something. The theorem just says that there exists such a function. For example, a similar thing, the intermediate value theorem or the mean value theorem you are taught in your high school maths or an undergraduate calculus. What kind of thing they talked about? Given such and such conditions, there exists some number in the interval a, b, and blah, 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 right? And it does not give you how to find given a specific example. It just says that you can find, there exists. Okay, got it? Same thing in Kolmogorov's extension theory. According to our Peebles book, sometimes you can exactly find that function. I may give you today that kind of homework problems after the class meeting or next week. And sometimes, given fully described random process, you cannot find this function. If I say that, hey, find this one, you may say that I can't. That's okay. Okay. The theorem says that there exists, guarantees existence. It does not says that you have to find that yourself. Got it? Anyway, so let's go back to this one. So, by the way, today there will be more classifications of random processes. As I told you in the last meeting, in signals and systems, we divided signals as some right-sided signal, left-sided signal, finite energy signal, finite power signal, systems as a linear system, nonlinear system, time invariant, memoryless with memory, blah, blah, blah. And some classifications and intersection of that classifications gave us very small set, given a large set of every possible continuous time, for example, systems. What was that? Continuous time, linear time invariant system. The set of continuous time linear time invariant system. And if we just focused on that, but we've got a lot of good structure there. Existence of impulse response that describes everything. Fourier transform of it called frequency response. Very useful, something like convolution. Got it? Same thing happens, and you will see. Okay, so here goes the stationarity and independence. And you will see the power of Kolmogorov's approach when you read this one. First, the question is this: how can you fully characterize statistically or probabilistically a random process? And now you know that there are two ways. The first thing, is what? Using nth order joint CDF or PDF, or if you want characteristic functions. Second one is what? You find somehow abstract probability space and that selection or mapping rule, that formidable function. So there are two ways. Which one do you prefer? Of course, the first one. So method one, you got it, right? Method two, I just mentioned. So it's like you choose any single random variable from the collection of jointly distributed random random variables, and you do it. You do the second thing, third thing, something like that. So a full characterization is what? Very complicated. Very, very complicated. You have to do this infinitely, right? So in general, a full description of a random process is very difficult. That I also mentioned at the end of last meeting. But some classes of random processes, this description is very easy. I already mentioned about this. So let's see some examples. Okay, before doing that, okay, got it. Some people, some authors of the book use this notation. I really hate, okay? But anyway, the Peebles textbook has this notation. Yeah, CDF, the capital F means the CDF. CDF of X. X is a random variable. And you have two arguments separated by semicolon. The left one is X1, and second one is T1. What does that mean? So in my undergraduate course, I preferred this notation. And now, suppose you are given a continuous time random process, capital X of T, and you fix T by T sub 1. Then what happens? Given at a specific time, you have what? Many, many sample paths. However, when they are all have sampled at T1, you are given a random variable, right? So this is a random variable. And now this is simply the argument of CDF of the random variable X of T1. And now you know from your undergraduate course, the CDF is defined in this way. X of T1 is less than or equal to this lowercase x1. And that event's probability, right? Okay, listen and repeat. The probability of an event. Yeah, this is very important. Many, even the graduate students, when I ask, hey, talk about probability, and they do not say, okay, the probability of event, that blah, blah, blah. You have to have that in your muscle memory, okay? The exact term is that the probability of the event of something occurring. Probability of event that something is happening, got it? So this is an event, okay? Event goes to the argument of the probability measure, got it? That is measure theoretic definition of probability, okay? You measure the probability of an event. Anyway, this is the kind of first order CDF. Then what is the second order CDF? Suppose you choose two time instances, T1 and T2. And then you have what? You have two random variables, right? Given a single continuous time random process, if you sample at two same or even, different time instance, then you have two random variables. And if you want, you may redefine this as one as x1, and you may redenote as x2. Then what? The second order or joint CDF or PDF of these two random variables are what? Something like this. Here, joint CDF of x1 and x2. They have two arguments. This is the notation, standard notation. And it means in terms of the event that capital X of T1 less than or equal to x1, capital X of T2 less than or equal to x2. this is the new event, okay? So if I ask you to put curly bracket, then you have to have left curly bracket here and the right curly bracket here. Because precisely speaking, this P, the probability measure of that abstract probability space, have to have a set as the argument. So people just use this notation, but actually there should be the curly brackets open and close curly brackets to mean that this is the event. But they just drop it, assuming that you all know that and we all agree that let's drop that. The problem is that most of the students do not know that, and professors do not emphasize that, so students has a lot of confusion. Okay. We will go back soon anyway. When I was a professor at University of Massachusetts, I was a kind of fresh PhD professor, and in my graduate level probability and random processes course, there was students from a prestigious university in some country, the #1 university in some country. And he had no idea about the difference between, for example, x = 1 and x = 1. Precisely speaking, this one meant for all s, and this one meant what? Probably many of you may say that, what? It's okay, got it? These are different. See that? Consider random variable. You have that second box in major theoretic definition. That box always maps for every s, output is 1. What does that mean? It's a kind of deterministic source that generates always 1. Second one is that I put curly bracket here and x = 1. What does that mean? This is a shorthand notation or abuse of notation that actually means this. You have a set of S, a member of the sample space, such that that mapping rule gives you 1. Got it? They are different. This is an event, and this may be defining that random variable is actually deterministic. That's different. He could not understand the difference, and he argued that it's correct again and again, and I said, okay. You know that, you win, okay? And what happened? After he got the master's degree there at University of Massachusetts, he applied to a graduate program of, you know, that the private university located in Cambridge, and he moved to that university. After that, I kind of do not much highly evaluate the students of that university at Cambridge, starting from M something Institute of T something. Got it. Okay. By the way, he was a class lab mate of Professor Byung-Suk Kim. Anyway, just a joke. Okay. Answer the distribution. Same thing. Just see that you have how many? Capital N jointly distributed random variables obtained by sampling a random process, capital N times. And so you have N arguments. And this notation means probability of event that first random variable realized as less than or equal to first argument, second random variable realized as the second argument, less than or equal to second, last random variable realized as less than or equal to this last argument. And you have your invisible curly brackets to denote that is an event. And many textbook, including the Peebles textbook, has this notation. So they say that, as you've seen here, where it is. Yeah, you have here a box. Here has a box with capital X of ST. So he called, okay, capital X is the name, and it has 2 arguments. So I put the first argument there in the first, second argument in the second place, something like that. Okay, so where it is? Yeah. So semicolon is a very useful separator, which seldom used by Koreans, right? Actually, I love using that one. Yeah, you may regard it as a kind of something little bit stronger than comma, okay? So it's like, okay, I love apple, mango, banana with commas and semicolon, then Diet Pepsi, Diet Coke, Diet Mountain Dew, and you may say that, okay, he used the semicolon to separate fruits and sodas, something like that, right? So freely use semicolon, very useful. I'm not sure whether that semicolon is really included in our Korean punctuation rule. I don't know. Anybody knows? Please let me know. Okay, joint densities are sometimes very useful. First order density over probability random process, second order density, third order joint density, and so the problem. Got it? And I believe that's not that difficult. And now here comes something strange. That is the expected value over random process. Probably we have to spend a lot of time to what's the meaning of this one. Okay. So let me ask you a question, because most of you have already taken an undergraduate course of probability and statistics or probability random process. What is an expectation? What is the expected value over random variable? Let's start from that one, because that's the simplest one, right? Whenever you have something new, what is your approach? You find something similar already in your mind or brain. And also you find what? Something as simple as possible. So random something, the simplest one. What is that? Random variable. Okay. So let me ask you, what is the definition, or what is the meaning of the expectation or the expected value over random variable, for example, X? And how can you compute that? Anybody? Yeah, everybody knows that. So recall, given a random variable X, expected value of X, which is denoted by this, got it? Expectation of X. By the way, there are a lot of confusions. This curly bracket does not mean event. That's the problem. If it is an event, this should be an event, but this is a random variable. Okay, so I definitely do not mean this to denote an event. So if you do not like that, use this one. By the way, I have many probability random variables, measure theory related books, and it seems that some mathematics professors really love round bracket. And that is kind of standard notation that you have an argument inside it, right? So I'm kind of have started to prefer using that one, but my old textbook says sometimes square bracket, curly bracket. So I'm sorry for the confusion, but here I use the square bracket. Got it? So what is the expected value of a random variable? And many of you say that, okay, according to my high school thing, I have an index I. Let me have some M and P sub I and X sub I. Okay, this is the definition. You are correct in a limited sense. So what do you imply here? You imply that your random variable X is a discrete random variable. What does that mean? Your outcome of this big box, your undergraduate random number generator, can generate only what? A number from a finite set with capital M entries. For example, you roll a die. Then capital M equals 6. And if you model it as a fair die, what do you have? P1, P2, up to P6, or 1 6th. And X1 is, for example, 1, X2 is 2, and X sub 6 is 6, right? So what is that? You can always interpret, because this is a very important thing, interpret the expected value of random something is what? Summation of, it could be finite sum, it could be countably infinite sum, or it could be actually uncountably infinite sum, which we call integration of what? A product. What is the product? This value times its probability, right? So value times probability. If you don't like that, I will write this way. Value, probability. Got it? By the way, why we were motivated to define this type of thing? Actually, it is motivated by the notion of center of mass, okay, in your physics, where we had, for example, in one-dimensional line, if we have capital M point masses located at x1, x2, x3, ... xm, and each point mass has mass m1, m2, ... m sub capital M, then what is the center of mass? How do you compute? You compute the center of mass as what? As what? Sigma summation index ranges from 1 to capital M, and its location, because the unit of your center of mass must be the same as unit of location of your masses, point masses. So value times what? Normalized mass. So sigma, okay, M sub, this use of M is very confusing. But anyway, I should have used N, but anyway, it's already J from 1 to M, and P, sorry, M, MI. Got it? So this one is the total mass, and this one is the mass corresponding to this Xi. And we may interpret this value as what? The probability. Because the sum of probabilities equals 1. Sum of this normalized mass equals 1, right? So the notion of mean or expected value of a random variable was motivated by the physical notion of center of mass. Got it? And now in your undergraduate physics, you extended this point mass idea to cover a distributed mass by introducing the mass density, right? So then, for example, suppose in one dimension, now you have some distributed mass, and this is, let me say, rho of x. Got it? So, for example, from x1 to x2, the total mass between this, on this interval is computed what? Computed as the integration of this density from x1 to x2, right? And now, if you extend this idea of expectation of, or the idea of the center of mass to distributed mass, what do you have? Almost the same thing. You may say that this x bar, the center of mass, would be well approximated by some summation of what? Xi prime and Mi prime divided by the integration of the entirety. And then if you divide the interval smaller and smaller pieces, then you believe that this summation will converge to what? Location times what? times the density. Okay, sorry, normalized by the density. Got it? And you may replace this one as, for example, P of X. And now you can extend your idea of the center of gravity to what? Expected value of a continuous random variable, right? So first thing, this expectation, the concept of expectation was motivated by the center of mass in physics, okay? And whenever you compute it, remember that expectation of some quantity equals what? Summation of that value. The expectation of some number is a summation of a number times the normalized density or probability of that value. So you have the same unit between this one and that one, got it? Because this is unitless quantity. Now, given that, our question, so what is the expected value or mean of statistical mean over random process? And I still remember my experience. I took that course when I just returned from the military service. So when I was a sophomore in the first semester, I took the probability and random processes course in the undergraduate program. And I studied very hard because my professor covered the Peebles book from cover to cover. In other classes, there were 3 parallel classes because we had a lot of students at the time. And one of the professors just talked about major theoretic definition of random variable to undergraduate students during the entire semester. So even he could not cover 2 random variables joint distribution. He just mentioned the sigma algebra throughout the semester. But my professor just covered the textbook from the first page to the last page. So it was very fast. But anyway, I did very well based on this, the soldier spirit. Okay. The problem was that in the next semester, when I was taking some other courses where random processes were little bit handled, I confronted this one and I got a shock because I could not remember anything. Hey, what was the definition of a random process? Expectation. What was that? And here, whenever you have some x of t, where t could be any number, like that, right? Fix that number, okay? That is a kind of way to simplify your idea. So let's choose t0. Then what is this? Expectation of x of t0. And you know that given a random process, if you sample at some specific t0, now you have a random variable. And you know what is the expected value of random variable. So this one must be, if it is a continuous random variable, integration of what? The value, integration variable x, and what? For example, the PDF of this random variable, dx, right? Now, what do you do? Okay, for arbitrary t, let me just delete this subscript 0. Done. So here comes what? The first order PDF of the random process. So in order to compute the expected value of a random process, you have to have the concept of what? The first order PDF, if you want to use PDF. If you want to use CDF, you have to have the concept of first order CDF of a random process. Got it? Now, what is that, by the way? After you compute this one, what do you have? You have a number parameterized by t, because if you change t, this first order density may differ, right? if you change it from T0 to T1, it could be different. Then what? You have a scalar parameterized by T. What is that? A function of T. So you may call this function, you may name this function of T as what? Let me use mu. But I want to be more specific. Okay, this is the expected value of the random process X. So let me put capital subscript X here. And this is one of the popular notation to mean the expected value of a random process X as a function of T. Got it? So let me ask you a question. What is the expected value of a random process? A continuous time random process. A continuous time signal. Then similarly, since you are graduate students, I'm not going to write down. Let's extend it. Given a discrete time random process, capital X of bracket n, what is the expected value of that random process? A discrete time signal mu sub capital X of square bracket n, right? Got it? So now you know what is the expected value of a random process, whether it is a discrete time or a continuous time. Got it? And okay, we have defined that. Now let me ask you a question. Then given a random process, how much information or knowledge does the mean of the random process provide you? So for example, we cannot fully describe statistically a random process X of T. However, we know the expected value of random process X of T. Is it enough? Your answer should be no, right? You know that from your undergraduate program, given two different, totally different distribution of a random variable, their mean value could be the same. Same thing here. Given totally different two random processes, their mean value could be the same. By the way, some people use mean path or mean function because they want to emphasize that this is not a single scalar. Okay, so this is a mean of the random process X of T or the mean function or mean path, as we call mean sample function path of the random process X of T. Okay, so be careful. The mean path does not give you the entire knowledge on your random process because it involves only what? The first order PDF, right? Joint distribution is very important in many cases. And many stupid thing occurs because we ignore the dependency between jointly distributed random variables, as you've already seen, right? For example, in your undergraduate program, you've plotted many points on the XY plane when you have a source that generates two random variables, X and Y. You observe one pair, X1, Y1. You observe the second pair, X2, Y2, and you put dots there, right, on the plane. And then you what? You draw two-dimensional histogram and you normalize that properly and consider kind of infinitely many generation and interpret that result as what? A two-dimensional density function, joint density function, right? And you know that two totally different distributed these dots means scatter plot may give you the same thing. For example, sometimes you have this ring and sometimes you have this straight line may give you the same first order PDF for X and Y, right? Sometimes, so let me just use Gaussian distribution or normal distribution. Suppose X is a zero mean unit variance Gaussian. Y is also zero mean unit variance Gaussian. And if they are independent, what happens? The scatter plot will look like what? A circularly symmetrical, but if you approach to the center, the number of dots will increase, right? So you have two-dimensional, that strange hat type thing, right? So, but what if x equals y? Then you have a straight line. But the PDF of x is n of 0, 1. PDF of y is n normal with parameter 0, 1. Same thing. So joint PDF is very, very important. You know from your undergraduate course, right? And your sample path or sample function of random process involves only first order PDF. So it lacks a lot of information. It loses a lot of information when you compute that one, but still important in many cases. Let me see some other cases before we move to Bernoulli random process, because that's complicated. So suppose you observe a random process, which means that you observe a single sample path somehow generated. It looks like that. And now in your parallel universe, now you understand, you observe another realization. And that looks something like that. And in another parallel universe, you observe something like that. Now you may say that, okay, it seems that every sample path in my parallel universes, they are all continuous time functions. However, it's possible that if your mean path may be discontinuous. It's possible. Okay. Somehow. Okay. And the converse is also true. Okay. Consider that. Suppose you have value 1 for the interval n to n plus 1, or value -1 from n plus 1 to n plus 2. And in the next interval, you randomly choose 1 or -1 with probability 1/2. So it's kind of a digital signal, right? Communication signal that takes 0 or 1 with equal probability. Every sample path is what? A discontinuous function, right? Somehow there will be some transition. However, what is your sample path? What is your mean path? Mean path is what? A zero function from -infinity to +infinity. So it seems that this mean path sometimes could be very, very misleading. Okay. My cell phone says shut up, but usually I have 1 more minute. So be careful, okay? This is very, very important, especially as a graduate student. Okay, you should never forget this. The mean path could be very strange, far from each sample path. It could have totally different property from your sample path or sample function. Sample functions, every sample path, or almost surely, almost every sample path could be discontinuous, but your mean path could be a very smooth continuous function. Sometimes your mean path may be differentiable, but your every sample path may be not differentiable. So be careful, okay? Sample path is a very important notion, but it could not well represent your ensemble of sample path. Got it? So mean path is a strange thing. It could be very useful in some cases. It could be very, very misleading in many cases. Okay, that's all for today.